the COVID pandemic. For 2 years, we've fought this invisible enemy on a hidden battlefield. In that time, we've lost close to 1 million Americans to this deadly disease. Most of my career, I've worked as a research scientist, also as a high school science teacher. My whole life I've been deeply involved with science. What I would like to do is show you the science of how we get this disease, how viruses infect us, how our bodies can protect us, and most importantly, how vaccines protect us from becoming infected with serious disease, even hospitalization and death. Now let's take a look at some of the data that shows us just how deadly this virus has been. Here we're looking at the trends in COVID cases across a couple of years. The blue bar represents the number of cases in every single day. The red bar gives us the average, and the orange bar shows us the total cases per 100,000. So in about early February, we hit a high of over 1.3 million cases in a single day. That's really catastrophic. And at about that peak, we were averaging over 800,000 cases a day for weeks at a time. So at this point, we're averaging almost 24,000 cases per 100,000 people. That is the highest incident rate in the world, higher than any other Western or developed country. Us, the US. And when we looked at the daily trends in deaths, not just cases, but deaths, it follows the same pattern. So here we see daily deaths, 7-day average, and the total deaths per 100,000. At the peak of the Delta spike, we had over 4,000 deaths in this country every day. And from mid-January to mid-February, for over a month, we've been averaging over 2,000 deaths per day, 2,000 Americans dying every day. And when we look at the total number of deaths, it's really astounding. We're approaching 1 million deaths. And when we look at the distribution of the number of the cases by age group, you see no age group is unaffected. Of course, the older groups are more vulnerable, and even though younger people tend to have less severe infections, at this point there are over 2.7 million kids between 5 and 11 who have been infected by this virus. By early January of this year, in La Plata County alone, we've had 566 cases in 0 to 9-year-olds infected with COVID. Yes, they are vulnerable. Now let's take a look at the science behind how our bodies protect us. We need to understand our own immune system. Innate immunity is what we're born with. It's really our first line of protection. And to understand that first line of protection, first we think about the barriers to infection. After all, where are we first exposed to pathogens? Well, it's what we touch, what we eat, what we breathe. That's how the virus gets into our bodies. Skin is a barrier to infection. Enzymes in our tears and saliva can protect us from various pathogens. Acid in the stomach can kill pathogens. The lining of the intestine is a mucosal barrier that protects us. The adaptive immune system is not very strong at birth, but as it develops the ability to recognize specific pathogens. The innate immune system is sort of non-discriminating. It attacks anything that the body doesn't recognize as belonging there. But as the immune system matures, it learns how to recognize specific pathogens, and then it can develop antibodies and specialized cytotoxic T cells that recognize those pathogens and attack them directly. And most importantly, our immune system develops a memory. In that way, when we encounter that pathogen months or even years later, our immune system remembers it. It remembers how to make the antibodies and the killer T cells that can protect us from that pathogen. Let's look at the details of how we create that memory and how we create those antibodies. This is an image of a macrophage. And the macrophage, you can see, is eating a bacteria. And it digests that bacteria. And you'll notice there are small orange circles on the surface of that bacteria. Those are generally protein-like structures, but they're structures that the immune system can learn to recognize them. We call them antigens. And those antigens are released, and we have specialized molecules in the macrophage that recognizes that antigen, binds to it, and then expresses it or puts it on the surface of the cell. And that is a signal for helper T cells to come and bind to that antigen. And in that way, the helper T cell will learn to recognize that antigen. And how does the macrophage get that T cell to come? It does that by expressing cytokines. These are chemical messengers, the way that immune cells communicate with each other. Not only communicate with each other, but how they actually coordinate their attack against the virus. And that activated T cell also sends out these cytokines to alert other parts of the immune system. So after the macrophage connects with the T cell and they secrete these cytokines, these messengers, that alerts a whole series of events. The T cell clones itself, makes lots of copies of itself, so there can be a lot of them to form the protection. And it alerts B cells. The activated B cells connect with that T cell. Then the B cell is able to eventually become a plasma cell and produce antibodies to that antigen. So some of those T cells, after they're activated by the cytokines, turn into cytotoxic T cells. These cells attack infected cells. The real key to adaptive immunity is that activated T cells eventually produce memory T cells. And activated B cells produce memory B cells. And these memory cells, they are probably the most important part of adaptive immunity. In this series of slides, I'm going to show you actual pictures of these cells in action. Here you see a macrophage eating a bacteria. Remember, the macrophage digests that bacteria so that it can isolate the antigen, and then it expresses that to a T cell, a helper T cell. Here you see an antigen-presenting cell, such as a macrophage, binding with a T cell. Then that T cell binds with a B cell so that that B cell can eventually produce antibodies against the virus. This is what's actually happening inside that B cell. And no, I don't really expect you to read that. I just want you to be impressed with all the multitude of pathways that are going on inside that B cell. And keep in mind, each one of these pathways was probably a single research project by a scientist or a research group. Now is a picture of antibodies, those white Y-shaped things, attacking a coronavirus. And they're binding to those spikes on that coronavirus, what we know as the spike protein. This is a depiction of a cytotoxic T cell attacking a cancer cell. It would be doing the same thing with a virus-infected cell. So if that cancer cell or virus-infected cell is killed, it won't be able to reproduce. It won't be able to reproduce those viruses. Now let's look at the natural course of an immune response. From the time we're first exposed, that process begins, and our body starts producing antibodies, and eventually it gets to that protective level. Once it gets to that protective level is when we're able to start defeating that disease. And you can see that it doesn't reach that protective level for about 2 weeks. After about 3 weeks, it gets to a peak. And after that, once the disease is controlled, those antibody levels drop down to well below the protective level. But remember that part of the adaptive response is that we have memory T cells and memory B cells, so that the next time that we're exposed to that virus, what we call a secondary exposure, and that could be days, weeks, months, or even years later, we have memory cells. And even though the antibody levels have fallen below the protective level and we become infected, because we have those memory cells, our immune system is able to mount a very robust response within days, not weeks, but days. So we very quickly suppress that pathogen and don't get very sick. Well, how does a virus cause an infection? Well, that virus has to bind to a receptor. The virus learns to recognize receptors on human cells, binds to that receptor, and then it injects its own RNA into the cell. It takes over the synthetic machinery of the cell, and then that cell starts reproducing the virus, many copies of the virus. And each of those viral copies then goes on and infects other cells. And because each cell that's infected produces thousands and thousands of the viral copies, within a very short time, there are millions of viral particles in our bodies. Well, how does a vaccine work? Well, a vaccine, it can be a dead virus. In other words, you can have a virus that is not able to reproduce, but it has a recognizable structure that the immune system can respond to. Sometimes it can just be a part of that virus, such as a viral protein. In the case of COVID, that protein is the spike protein, which I'll explain more in a minute. Either case, the immune system recognizes that protein or that dead virus as a foreign antigen. And once it has that recognition, it can go on to make antibodies to that antigen so that we're protected. Here's a picture that we've come to recognize so well. Can't say we're fond of it. It looks so pretty and innocuous there. And all those red structures, those are the spike proteins that we hear so much about on the surface of the cell. And the spike protein is what recognizes the receptor on human cells. In the case of the coronavirus, that receptor is called the ACE2 receptor. In this micrograph, you see the ACE2 receptor, and here you see the spike protein binding to that receptor. Once that receptor has been bound by the spike protein, that's when the infection begins. To really understand how some of these vaccines work, it's important to understand protein synthesis. So we're going to go back to a little high school biology here. I'm sure you all loved high school biology. This is a cell, and in the nucleus of the cell is the DNA. The DNA carries the instructions for all the proteins that that cell is going to have to make. And say the cell gets an order for a certain protein to be made. Well, the DNA takes the part of that message that's the instruction for that protein and translates it onto a message, messenger RNA or mRNA. The mRNA leaves the nucleus, goes out into the cell and finds a ribosome. The ribosome is the protein factory of the cell. Then another type of RNA, transfer RNA, brings amino acids, which are the units of a protein, to the ribosome so the ribosome can synthesize that protein. If I can give you an analogy, let's say that that cell is actually a chocolate factory, and the DNA of that chocolate factory would be the recipes for all of the chocolates that that factory can make. Someone puts in an order for a truffle. Well, the DNA will then give the specific recipe for the truffle, or mRNA, out into the factory. And then the transfer RNAs would be the ones that bring the ingredients to the assembly line, the ribosome. Then once all the ingredients are there at the assembly line, it can produce a truffle. Now let's look at the mRNA vaccines made by Pfizer and Moderna. The technology for mRNA vaccines really began over 20 years ago. The real breakthrough came just over the last few years when scientists learned how to protect that mRNA from enzymes in our blood that would destroy it. In order to do that, they discovered that they could put that mRNA in a liposome, or a fat bubble. They made the messenger RNA for the spike protein. And this was done very quickly. Once the first virus was isolated and its genetic code decoded, they were able to take the message for the spike protein, put it on an mRNA, and place it inside that fat bubble. That fat bubble is then able to bind with the surface of a cell, a human cell, and release that mRNA into the cell. And the mRNA seeks out a ribosome and then binds with that ribosome, and that ribosome then starts making many copies of that spike protein. And that spike protein is then expressed on the surface of the cell so that an antigen-presenting cell, that immune cell that recognizes the spike protein, starts the process of communicating with T cells and B cells in order to make antibodies against that protein. The AstraZeneca and J&J vaccines are a little different. They use something called the adenovirus. This particular adenovirus is similar to a dead virus. It can't really reproduce itself, even though it is technically still alive. And then the researchers make viral DNA. It's a recombinant DNA. It's synthesized, and it contains the instructions for the spike protein. When the virus then enters the cell uses that viral recombinant DNA to make copies of the spike protein, which then initiates the whole process of antigen recognition and antibody production. We hear a lot of terms connected with vaccines. How efficacious is it? Well, what is efficacy? Let's look at the data from the J&J vaccine trial here in the US. There are two arms to the study. The placebo group, people who are injected with probably a saline solution, not the vaccine. And in that group, out of 5,000 volunteers, 63 became infected with COVID. In the vaccinated group, only 18 out of 5,000 people became infected. That's 72% fewer cases in the vaccine group compared to the placebo group. That translates to 72% efficacy. Let's look at the mRNA vaccine for Moderna. Its efficacy in preventing illness, in other words, getting infected, the vaccinated group, only 55 out of over 15,000 people became infected. And in the unvaccinated group, over 700 out of 15,000 became infected. Well, that translated to an efficacy of 93.2%. But what's more important is how effective it is in preventing serious disease. In the vaccinated group, only 2 out of over 15,000 people became seriously ill, while in the unvaccinated group, over 100 out of 15,000 became infected. That's an effectiveness of 98%. Over 98% effective, that is pretty remarkable. What about the Pfizer mRNA vaccine? Let's look first at efficacy against infection. 3 weeks after the first dose is administered, about 35% effectiveness in preventing infection. But a month after the second dose, that rose to over 75%. But if we look at 6 months after the second dose, the efficacy drops to about 15%. Now remember, when we looked at the normal response of the immune system, after that peak of antibody production, remember the antibody levels fall below the protective level. But what's more important is how effective it is against severe, critical, or even fatal disease. And 3 weeks after the first dose, it was about 65% effective in preventing severe disease. 2 months after the second dose, that rose to over 95%. But look at 6 months after the second dose. That did not drop, because remember, we have memory cells. So even though we may have antibody levels that have fallen to the point where you can become infected, our memory cells kick in and we are fully protected against severe, critical, or fatal disease. So efficacy is the percent reduction in actually becoming infected, catching the infection. But the effectiveness is the ability to prevent outcomes in the real world, what we're really more concerned with. How well does it protect against serious disease, hospitalization, or even death? Now, of course, there are a lot of treatments available. The one that's got the most interest are antiviral pills. There was an earlier treatment, monoclonal antibodies, and these are antibodies against the virus. But this treatment required an infusion, and that had to be done in a hospital. These antiviral pills, on the other hand, can be taken at home. So the antiviral pills have to be initiated within 3 to 5 days of actually becoming infected. And then they're taken for about 5 days, which is a much simpler thing to take pills at home than having to go into a hospital for an infusion. 2 companies have made antiviral pills, Merck and Pfizer. If we look at the percent reduction in hospitalization a month after the treatment with these pills, the Merck, there were 30% reduction in hospitalizations with 1 death. And in the Pfizer pill, there were no deaths and an 85% reduction. The real challenge with these antiviral pills is because they're relatively new to the market, manufacturing has not yet caught up to the demand. So they're not readily available for everyone and generally are given only to the most vulnerable. A good way to understand protection against infection is what's called the Swiss cheese model for virus protection. I know, it does sound cheesy, but think about a block of Swiss cheese and you cut it up into slices. Well, the first slice, kind of a personal thing, might be just social distancing, keeping far away from people, or if you start to feel ill, staying at home. Then the next most important level are masks that really not only protect you from getting the infection, but also protect others from getting infected if you have the disease. Simple things like washing your hands, coughing into your arm instead of out into the open, not touching your face after you touched a possibly contaminated surface, avoiding crowds. Crowds are where the virus is most likely to be spread easily. Testing so you know if you've been infected and to take extra precautions. Because this is an airborne infection, room ventilation makes a massive difference in the rate of transmission, or being outdoors where the virus can't easily find a host. The government can provide support. Lately, we see the government sending masks and testing equipment. If you do get sick, quarantining is very effective in preventing the spread, or isolating in your house if someone else in the house has the infection. And then the final slice, vaccines, the most effective protection of all. Vaccines have been around for quite a while. The first vaccine was actually in the late 1700s, when smallpox was a horrible disease that had very significant mortality. The vaccine was called a cowpox vaccine. Cowpox is a disease similar to smallpox that infects cows, but not people. And by inoculating people with the cowpox virus, it was similar to using a dead virus. It had enough similarity in structure that the immune system could provide some protection. And some of the fear-mongering that went on at that point looks kind of hilarious at this point. Here you see a young woman attacking a patient with a cow, the cowpox. And this is one of my favorites. You see scientists shoveling something into the mouth of the distorted cow and pooping out some kind of vaccine. Well, here we are 200 years later, and we still see the spread of misinformation about vaccines, their safety and their effectiveness, and all that is misinformation with no basis in fact. In fact, the first vaccine mandate was from George Washington. At that point, he instructed his Surgeon General, Dr. William Shippen, and he ordered him to inoculate all the troops that came through Philadelphia. He recognized the necessity not only authorizes but seems to require the measure. For should the disorder, smallpox, infect the army, we should have more to dread from it than from the sword of the enemy. In fact, many historians credit this vaccination campaign with the success of the Revolutionary Army. The British Army didn't get the vaccine, and they suffered catastrophic losses from smallpox, a huge advantage for the Revolutionary Army. So here are the vaccines that are currently recommended by the American Academies of Pediatrics, Family Physicians, OBGYN, and you're probably familiar with these. There's really no public memory of what these diseases are like because they have been defeated. How often do you see a case of diphtheria or tetanus or whooping cough? Vaccines are effective. They have defeated these diseases. And the only time we see them pop up again is in cases where there are groups of people who have decided not to get vaccinated. And what you don't see there is smallpox. No one gets a smallpox vaccination anymore. Why? Because the vaccine was so effective that it has essentially eliminated smallpox disease from the entire planet. These vaccines are extremely effective and they protect us against getting those diseases. The coronavirus is particularly infectious because of the way it's transmitted. It's transmitted through the air, what we call aerosolized airborne transmission. Here you see a picture of someone sneezing or coughing, and that red are all the drops spewing out during that cough or sneeze. But what's particularly problematic is that in that sneeze or cough, there are tiny, tiny droplets less than a 10 millionth of a meter in diameter. And those droplets can contain the virus. And because they're so tiny, they can remain suspended in the air for hours. When someone coughs into a room, that room can remain infectious up to hours later. There are now at least 11 published studies that show the efficacy of masks. And you're not just protecting yourself, you're also protecting others around you who may be exposed to the virus if you were to spew out those viral particles unimpeded. We see a lot of different symptoms from this COVID virus. What we're used to with the flu is a very specific set of symptoms. But in the case of the coronavirus, that ACE2 receptor, it's all over the body. It's not just in the lungs, which is where it's most plentiful, but even the ileum, part of the intestine. It's in lymph nodes, the kidney, even the heart. Depending on where the virus proliferates to the greatest amount can determine what your symptoms are. And let's take a look at a heart infection. Here you see a micrograph of human heart muscle cells in red, and all that green, that's the COVID virus. In fact, this wide distribution of COVID receptors all over the body probably accounts for some of the effects seen in long COVID, effects that are seen for months and even a year or more after the infection. You recall I just showed you there were ACE2 receptors in the brain. And here we see that brain inflammation and low oxygen levels can cause long-term cognitive effects. A recent study that looked at the risk of mental disorders in 150,000 patients who had COVID for 30 days.
COVID hospitalizations are on the rise again today.
They looked at anxiety disorders, depressive disorders, stress and adjustment disorders, antidepressant usage, substance abuse disorders, neurocognitive decline, and sleep disorders, and every single one was significantly higher in these patients. There are also long-term effects in the lungs, early evidence of oxygen limitations that can lead to fatigue. There are circulatory system effects. There can be vascular damage, blood clots that can trigger fatigue. And also the immune system. Yes, even the immune system can be affected. Autoantibodies and viral remnants can set off chain reactions that affect your ability to respond to other infections as well. What we're really seeing is evolution in action. So just think about how long it took for the woolly mammoth to evolve into an elephant. Well, assuming they have a gestation like an elephant, about 22 months, they produce one offspring. Well, in order for that change to take place, it took millions of years. With the virus, that mutation into a new variant is a much faster process. The replication is within hours, and millions of offspring are produced. So that evolutionary change takes only days to weeks. The reason these new variants are important is that they have to have some advantage over the previous variants. But they only get established if they can find an unvaccinated host to infect. That's the real reason why vaccines are so important, especially now. If there are large numbers of unvaccinated people, that means these new variants can take hold and spread disease. But what happens if a new variant arises that is resistant to the vaccines? Fortunately, with mRNA technology, as soon as a new variant like that would pop up, all we need to do is sequence the genetic sequence for that virus, and we can make a new vaccine. Although it takes much less time than in the past, it still gives that virus an opportunity to spread and cause serious disease, hospitalizations, and death. So here are the variants that we're most familiar with. Of course, the first one, I believe, was Alpha. Then came the Delta variant out of India, and that spread much faster than the Alpha variant, and it caused more severe disease. That was the spike that we saw last summer. Then the Omicron variant arose out of South Africa, and that spread even faster than the Delta variant. Now, although it doesn't seem to be as severe as the Delta variant, because it spread so fast and so many people were infected, the number of hospitalizations and deaths were even greater than the Delta. And now a new variant has arisen, Omicron 2B. Some scientists think it should get its own Greek letter, also out of Africa, spreading faster than Omicron. Severity is still a bit of a question mark at this point, although one study out of Japan, a laboratory study, indicated that it was possibly more severe, it bound more tightly to cells, and may be resistant to some of the antiviral medications that we have, although it does seem to be susceptible to the current vaccines. You can also see the effectiveness of vaccines in this graphic. This shows the COVID-19 deaths, and the part of the country where we see the greatest number of deaths is also the part of the country with the lowest vaccination rate. When large numbers of people aren't vaccinated, it gives the virus the opportunity to spread and cause serious illness. We can see that when we look at direct data. Here we're looking at hospitalization by vaccination status in adults throughout the entire country. So this line shows you hospitalizations in the unvaccinated and here in the vaccinated. That sharp peak at the very end there is the beginning of the Omicron surge. It's pretty evident from this graphic that if you've been vaccinated, your risk of being hospitalized is dramatically lower. We can also see this with the vaccination gap in hospitalizations during New York City's Omicron surge. Unvaccinated on top, vaccinated on the bottom. So this covers the onset of that surge. And once again, you can see that people who are vaccinated are at much lower risk of being hospitalized. Nursing home residents are perhaps the most vulnerable population. So this is particularly instructive. Here you see the number of cases in nursing home residents who are unvaccinated. Here are those who received the primary course of vaccines. In other words, 2 of the Pfizer or Moderna or the J&J. But if they got boosted, it goes down to almost 0. And remember, the benefit of the booster is not only in increasing the number of antibodies, but more importantly, increasing the number of memory cells. And once again, you may become infected, but if you have enough of those memory T cells and memory B cells, your immune system will ramp up very quickly and prevent any serious infection. In fact, I had a breakthrough infection. I got the Pfizer vaccine and the Pfizer booster, but I did get the Omicron variant. And it was no big deal. It lasted about 3 days, and it was like the annual cold virus. That's because I have those memory cells that were able to control that virus infection, so it never became anything serious. Now let's talk about kids. The Pfizer vaccine has been authorized in 5 to 11-year-olds. This is the data from the study that the FDA used to give approval for that vaccine. So we're looking at the cumulative cases of COVID as a percent of subjects. You see after the first dose that the number of children in the vaccine group who became infected was about 1/10 of those in the placebo group, and that held all the way through the second dose. To put some numbers on it, after that second dose, in the vaccinated, only 3 children out of over 1,300 became infected, while in the placebo group, 16 out of about 660 became infected. Again, a huge difference of infection. What many people are more concerned about is how children respond to the actual vaccination, not in terms of infection, but in terms of ill effects. And of course, the most common is pain at the injection site. After the first dose, it was about 70% in the vaccinated group and about 25% in the unvaccinated group. Even in the placebo group, they're still getting an injection. It's a saline solution. And yes, it hurts to have a needle stuck in your arm for some kids. And after the second dose, we see about the same response. What people are most concerned about are adverse events. When a clinical study is done, the study coordinators are required to record any adverse event that occurs in the course of the study. And that's anyone who is enrolled in the study. What the FDA requires are what are called intent to treat studies. That means you include in the data everyone who is enrolled in the study. Let's say you enrolled someone in the study and the next day they moved to Timbuktu. They were enrolled. You intended to treat them. Therefore, you have to include their data in the study. That makes the data very messy, but it gives you a lot of confidence that when you do see a significant difference, you can be sure that it's real. Any adverse event that is reported to the study coordinator must be included in the database. Here are the percent of subjects. So only 3% of subjects in the vaccine group reported an adverse event, about 2% in the placebo group. Only a 1% difference between the vaccinated and the placebo. And those adverse events included pain at injection site, fever, fatigue, headache, chills, vomiting, diarrhea, muscle pain, joint pain, use of anti-pain medications. As far as severe adverse events, less than 0.1%. A tiny fraction of infants, or children rather, who got this vaccine had a severe event. And even when we look at the morbidity and mortality report from the CDC, we see that at that point, 8.7 million 5 to 11-year-olds had been vaccinated. That's a pretty big number. And there were only 4,200 or so adverse events reported. 97.6% of those were not serious. So there was about a 17,000% of a chance of a serious reaction. And half of those serious reactions were fever and vomiting. So again, the safety profile of this vaccine is exceedingly good. Let's take a look at the attitudes of parents as to how they feel about getting their children this vaccination. This is data from 2021, and back in July, about 25% of parents said, yes, we'll have our kids vaccinated as soon as it's available. About 40% thought they would wait and see. I'm not sure what they were waiting for, but they wanted to see more data. Another 5-6% said they would get the vaccine for their kids if it was required, and about 25% said no, they're not going to get the vaccine. That data didn't change too much by September, but by October, you can see that about 73% of parents were either reluctant to or didn't want to get the vaccine. Why is this a problem? All those unvaccinated children represent a pool of hosts that a new variant can infect and then spread and cause more severe infection. Although children do have a much milder case of the disease, they are equally efficient in spreading the disease. So once again, unvaccinated children add to the number of people that allow these more serious variants to take hold and spread. When you're considering whether or not to get a vaccine, you need to weigh the risks versus the benefits. And what are the risks? Well, it could be a mild infection, but it could be severe illness. Loss of taste and smell are common. People talk about foggy brains. There could be long COVID that has, in some, lasted up to a year. And then, of course, hospitalization and even death. The vaccine has been proven safe and effective. It significantly reduces infection, hospitalization, and death, and this has been shown in millions of people all over the world. Yes, we are struggling through the COVID pandemic, and it's not going away. Now we must think of it as the COVID endemic, a virus that we will have to live with. Even in some viruses that we've controlled, like the measles, the measles virus didn't disappear. And where we see areas of the country where measles vaccine has dropped significantly, measles pops up again. This virus is likely to be with us on a permanent basis, but that doesn't mean that we can't control it. It doesn't mean that we can't be better at protecting ourselves against serious disease, hospitalization, and worse of all, death. Well, here are some common questions I get after I do my talk. Why do I need to wear a mask if I've been vaccinated? Well, you may have a subclinical infection. In other words, you may be asymptomatic. You may not even know you're infected, but you still could be able to prevent the transmission of the disease. And remember, the benefit of the mask is not only in protecting yourself, but protecting others from being infected. Another question I get is, why should we trust these vaccine companies when they're obviously doing this for a profit? Well, yes, of course. All companies have their business in order to make a profit. You pay your doctor when you go to visit him. If you're building a house and you want to find a contractor, you look for the best one. They may cost a little more, but you want the best possible outcome. And these companies are very good at what they do. Again, think of all the vaccines that are on the market now that prevent all those common childhood illnesses many my age had to suffer through when they were children. What you're paying for is a life-saving medicine. And in addition, many of these companies have donated millions of doses to developing countries around the world. Weren't these vaccines rushed into production? Isn't that a safety concern? Keep in mind that the technology for these vaccines has been in development for over 2 decades. And once they understood how to protect that messenger RNA, the ability to produce the vaccine was very, very quick. Normally, in the past, in order to get a medication approved by the FDA, it had to go through a series of 3 or 4 different studies, end to end. What these companies did, because it was such a national crisis, is that they did these steps simultaneously, which allowed them to dramatically shorten the amount of time it took to ensure the safety and efficacy of the vaccines. A lot of people are wondering why the CDC is always changing its guidelines. The CDC bases its guidelines on science. Science is a living process. It's not set in concrete. The beauty of science is that when you learn new facts, you adjust your hypothesis based on the new facts. As we learn more and more about the vaccines and about the spread of the disease, the CDC was able to change their guidance to be more realistic with the new facts that emerged. Another question is, how can someone get sick if they've been vaccinated? Doesn't that mean the vaccine doesn't work? Well, remember, even if a vaccine is 95% effective, that means that 1 in 20 people is not protected. No vaccine is 100% effective. There are always going to be individuals who are not able to mount a protective response to that vaccine. But once more, the critical thing is how effective it is in preventing severe disease and the spread of disease. And as long as there are unvaccinated people, new variants that are more deadly can spread and take hold. But once you've been vaccinated and you have those memory cells, you're protected from severe illness and hospitalization and death. It's much more dangerous. The seriousness of COVID is not something to be ignored. It is much, much more serious than the flu. Although the flu can be deadly, people do die from the flu, it's usually the most vulnerable, elderly, people with underlying conditions. With COVID, healthy people are getting sick and dying. In a really bad flu season, maybe we see 30,000 deaths, which is no small number. With COVID, we're now approaching 1 million deaths in 2 years. It is much more serious than the flu. Unfortunately, some people are resorting to alternative treatments. Most common are ivermectin and hydroxychloroquine. These are very effective medicines, but not for treating COVID. Ivermectin is extremely effective in killing parasites, and it controls parasitic disease. COVID is not a parasite, it's a virus. Hydroxychloroquine, That's really a synthesized version of quinine, what we use to fight malaria. Yes, it's very effective for that, but it is not effective for treating COVID. How do we know that for sure? Because there have been randomized clinical trials performed to test whether these medications do have any efficacy, and they do not. They are not efficacious against COVID. Vaccines are efficacious.